sorry about that, technical difficulties. So where was I? We were talking about writing the equation for this parabola, and we know the x-intercept, so we're using intercept forms. So that means y equals a times the quantity x minus b times the quantity x minus q, and p and q are going to be our x-intercepts. Well, conveniently, we know those. So the 9 and 1 are what we're going to use for our P and Q. So we'll use 9 for P and 1 for Q. Totally doesn't matter which one is which, it's fine. So we're going to put the 9 over here and the 1 over here. The reason it doesn't matter is because we could use the commutative property and flip-flop those two factors. So we're just going to put them in there. So we are going to have y equals a times the quantity x minus 9 times the quantity x minus 1. So we are most of the way to having our equation written for this. However, we still have an a. We need to have a number there. I don't know what the number is. It doesn't tell me that, but it does give me this other fact that this parabola happens to pass through the point 0, negative 18. Well, anytime you see an ordered pair, you know for sure that that's telling you an xy pair. So we have this x and this, what color have I not used? Oh, I don't know. I guess we'll just use, I guess yellow is fine. Can you see that? Negative 18 is our y. So we can plug those in as a way to figure out our a value here. So I'm going to put the negative 18 over here, and then the 0 is going to get used twice because I see two x's in my equation. So that's where those are going to go. So we are going to have negative 18 equals a times 0 minus 9. Oops, that was supposed to be 5. Times 0 minus 1. Okay, so I've got stuff filled in here. So in this first parentheses right here, I have 0 minus 9. That's just negative 9. So I have negative 9 getting multiplied by this other parentheses. 0 minus 1 is negative 1, and that's getting multiplied by a. And I know that this is supposed to come out to a negative 18. Okay, so we're working on figuring out what a is here. So if I do this multiplication, negative times negative turns a positive. So I have 9 getting multiplied by a. So this right side simplifies to a 9a. And on the left side, I still have the negative 18. So to get the a by itself, I just have to divide. So I'm going to divide both sides by 9. Those cancel, and a equals negative 2. So we were trying to write the equation here, so let's go ahead and get this equation written. So we're using intercept form, so I'm going to write it again so I can see what it was and I can remember where I was at. So we had already known our P and Q values. We had already filled those in. So we were at this point. We had x minus 9 and x minus 1. And now we know our a value is a negative 2. So I'll go ahead and put that in here. And ta-da! We have an equation for this line in intercept form. Now let's suppose you looked at multiple choices on this and it gave you standard form. Well, could you take this and change it into standard form? Yeah, you could do that. It's just multiplying it out. You know how to multiply binomials. You've been doing that since Algebra 1. So you'd go ahead and multiply it out, distribute that negative 2 after you multiply your binomials, and you'd be fine. But always choose the form to use based on what you know in the situation. Don't choose it based on what you want it to look like at the end. You're using it as a starting point to get into the equation first, okay? So choose it wisely. The last thing I want to show you is how we can use this in situations where we have data. So we are going to see if we can use quadratic regression if we deem that a quadratic function would fit this data. So let me show you some data that I have over on Desmos for us. Oh, I forgot to prove to you that that second case worked. Let me do that real quick. Oh, whoa, something's being weird. Pause. Okay, I don't know what was wrong with that graph there. We're going to skip over that graph. So what I have here is some data about different velocities of cars traveling. So the x's here are velocities in miles per hour, and then the y values that you see tied to those are the braking distance, how long it takes to come from that speed to a complete stop. Okay, so this is useful for police officers if they come upon an accident scene and they have like some braking skid marks that they can measure. They can get the speed of the car at the point at which the person began braking from that. I have this data here, and just looking at lists of numbers, I have no idea what this relationship is going to look like. I don't know if this is going to make a line, a parabola, some other curve that I haven't told you guys about yet. So we need to see this. So I'm going to graph this data for us, so I have it entered in a table on Desmos. So, what I did to get that table is I went up to this plus sign where it says add, and I chose table. So that's how you'll do that. Then there's this little magnifying glass, and it says zoom fit. So if I click that, it will show in my graph where my points are. Okay, so when I look at these points, they don't really look linear to me. It's not really making a line. It's kind of picking up as it goes, like it's getting steeper as it goes. So I'm thinking that would fit part of a parabola. So if I look at it and I think, yeah, I think this is fitting a curve like a parabola, I want to know what that curve is. Here's how you tell Desmos to make that curve, or to find the equation for the curve that would fit this. We're going to put y1 is approximately equal to, so this little wavy line on my keyboard is next to the 1. So it's probably somewhere up by escape on your keyboard. And I'm going to type in what is going to look almost like standard form, because ax1 squared plus bx1 plus c. Okay, so it almost looks like standard form. You're used to seeing ax squared plus bx plus c. The subscripts, those are the little numbers that I put down below. The x1s, I have twice, and y1. The purpose of those is to tell Desmos to tie it to this table here. And this table has an x1 and a y1 at the top. So that's what I'm telling it to use. Use those numbers in the table. So what you see is this curve here, that fits pretty well. And then the value of that is down below. The computer has figured out for me what the A and the B and the C would be in standard form for this curve to fit. So it's generating that for me so I could write my equation from that. The reason this is useful is then what if we come upon an accident scene and say that the braking distance, the marks on the road are 250 feet long. That car would have to have been going pretty fast. What we can do is find where our y value is 250. In fact, I'm going to do it this way. I'm going to say my y, because that was the column that was about my braking distance. We're going to say it was 250. So that point is where the x is almost 75. So that means that car would have been going 75 miles per hour at least. So anyway, that's how you can use quadratic. It's called quadratic regression when we get the line or the curve to fit by using the computer, and it's the best fit possible. Might not be an exact fit, but it's going to fit as close as the computer can calculate that. We saw that with linear regression before too. So those are the ways you're going to use quadratics today. You're going to do this page in your packet, and I'll put some problems on Canvas, which problems you're going to do there. So, well, I think that's everything. So remember, Jesus loves you, and so do I. So do your math.